So, hi everyone. Corentin and I will present you our project of the last semester about a portable method to record and display the color of the surface in collaboration with Damien Mouzelet, researcher of Hubert Laboratory. Okay. Let's begin with an example. Imagine you like this sofa. Actually, you fell in love with this sofa because you love the color, and you took a picture of it in order to remind this color. And there is something we don't know, is that your phone, due to the camera and the screen, change a little bit the color of your sofa on the picture. You can see there the true color of the sofa, and there a little bit different color. Actually, it's a picture that I took with my smartphone of the picture of the sofa on my computer screen. And my camera changed it. You can see that my camera changed a little bit the color. And that is what Damien Mouzelet wants to the problem. It's a problem that Damien Mouzelet wants to change. He wants to develop an application that is able to find the true color of something. And our goal here was to do a proof of concept of that. Okay, so our setup, there is 3 things in our setup. The first thing is a projector that is able to project a different color with known values of red, blue, and green. The projector projected the color on a grid of 24 squares of different colors. For the presentation, we will do a focus on this color to do an example. And after that, with the camera, we register the values of red, blue, and green of the color on the blue of the cyan here under a white illuminant, and the color of the white square under some colored light.
Okay, so our goal is to find when the white patch under a certain source is the closest to the colored patch under a white illuminant. So we want to calculate this norm with the RGB values linked to each patch. And for this project, we make the hypothesis that we have sources with the same energy, so with the same RGB, same norm for their RGB values. And with this hypothesis, we can write the source output, so what we will get on our camera, the RGB values, as the product of these 2 terms here. And when we develop this norm, we get this expression. And this term will be constant because of our hypothesis. The second one is constant on the measure, and the last one can be written as the sum of the RGB values on the sensor. And in theory, when we plot this norm squared in terms of the sum of the RGB values, we get this kind of graph. And our goal is to minimize this norm to find when we are the closest to for the 2 colors. So we are in this zone just right here. Actually, in practice, we couldn't manage to have equinergetic sources because we didn't have enough time. So we got rid of this hypothesis, but we kept its implication. And instead, because right now this term will change for each sources that we would use. Instead of plotting the norm squared, we will plot the norm squared minus this term that will depend on the energy. And that's the kind of plot that we will get, that we got. And when we look at the lowest point here, we get this color on a watt patch, which is actually very, very close to the cyan color under the white illuminant. So even though we have made a very strong hypothesis because we just get the consequences without the ecoenergetic hypothesis, we still have a very good result. So it's a good thing for the future of this project. Thank you for your attention.